Yes.
Okay.
All right, welcome everyone. Thank you for joining us today for our senior design presentation of AI for smart cities, pedestrians, and bicycle safety. Our sponsors are Los Angeles Department of Transportation, City of Los Angeles, and Toyota Mobility Foundation. Our faculty advisor is Dr. Mohammad Pourhomayoun. My name is Haley Gray, and joining me is...
I'm Marcio Arakaki.
Alejandro Bernal.
Freddy Gutierrez.
Hello, Matthew Ramos.
On today's agenda, we will briefly discuss Vision Zero goal, our utilized technologies, data analysis and visualization, along with our projects for this past year. We've been a very prolific senior design team and have 5 projects to share with you, including mobile and web apps for safest navigation paths, a bicycle collision visualization and analysis app, and mobile and web apps for Metro Bike Share historical data using visualization and analysis. If you work for the City of Los Angeles, you're probably very familiar with Vision Zero, its commitment to eliminate traffic deaths by 2025. Our projects capture the spirit of Vision Zero and aim to provide insights for better bicycle safety. We use data analysis and visualization to review accidents, routes, and stations, hoping to find patterns of showing where accidents are most frequent, how stations are used, and which routes are safest for bicycle navigation. Some of our technologies used include ArcGIS mapping and visualization framework, Los Angeles GeoHub, Python, Jupyter Notebook, Metro Bike Share data, including historical data and real-time data, Google Maps API, JavaScript, Android Studio, Node.js Express, and Pug Template Engine.
Good morning. My name is Alejandro, and I'll be introducing some of the data sets that we use for our safest paths implementations. As you can see to the left, we use the Metro Bike Share data available to us via the Metro Bike Share app, web app. We use this data to provide the user with all the locations of each of the stations available through Metro Bike Share, as well as we conjoin to using GeoHub data, collision data that's provided to us via Los Angeles GeoHub in order to get all the traffic accidents involving bicycle accidents and also traffic collisions involving pedestrians. We use this data set as our historical data set in order to build our algorithm that will create a safe path rating for the user to use the different options they have. Next, I'll go ahead and we'll demo safest path, but the web application version of it. As you can see, our website consists of a map view that contains all the information of our given to us by Metro Bike Share. So all the stations are there. As you can see, if you hover over a station, you get the information for such station. To the right side, we have a list view, and at the top left corner, we can see that we could filter data by city. If we filter depending on Echo Park, if we go to Los Feliz, we could see all the stations available to us at that location. And we could always go back to all the data. In our list view, we are able to see all the information available to us by the station. So it is an overwhelmingly large list. However, you could go ahead and we added a feature where you zoom in and it uses the maps web view in order to just show you the specific stations within that part of the map. So as you can see, the list shrinks down to the 6 stations that we have available inside our map view, and we could toggle on to those to check the information and verify that those are the stations. Next, we'll go ahead and show you what we could do with users' location. With our users' location, we could give users the ability to get from their location to the station. That's the most the basic utilization of direction, as well as render a nice convenient view for them to see how to get to that station. If we reset our map, we will show you why safest path is also different. So on this next feature is where safest path uses the historical data in order to give you the best path possible. So let's say you're the user and wants to go from one station. You get a station, let's say over here to the left. You'll be able to go from that selected station to another station anywhere in Los Angeles. Let's say you want to go for a long ride, but you want to do it the safest way possible. So using our historical data, it gives you the safest route depending on the safety rating. You can see that the first one it rendered will be the worst path. It is the shortest one, but it has the highest accident rate. Well, as you go to the green one is a little longer, but it's a safe path to take. And this is how safest path, the web app, works. I will go ahead and hand it down to Freddy. Freddy will be introducing our Android implementation. Thank you.
All right. Thank you, Alejandro. So here we have the Android version of our web app. There are some slight differences, such as our login or sign-up screen. User authentication is handled by Google's Firebase authentication, which checks for valid emails and passwords, and user data is stored in the Firebase database. Attempting to sign up with an invalid email or password will prompt the user with a toast saying authentication failed. Once an account is created, the user is redirected to the map centered around Los Angeles. Similar to our web app, the user can filter stations by cities, as seen here. Clicking the location navbar icon at the bottom will prompt the user to access their location. Granting permission then drops a marker at the user's location and highlights all stations within 1 mile of the user blue. After granting location permission, the user can click on a station to get walking directions from the user to the selected station. Clicking on the directions navbar icon will display directions of the current route. Clicking the pads navbar icon will prompt the user to select 2 stations on the map. Clicking on a station changes its icon so that the user knows which station is the starting station and which station is the ending station. Once the user has provided both stations, a safety rating is calculated for each route by checking to see which accidents are within a 1/3 mile radius of the route. If an accident is within the radius, its weight is recorded and associated with that route. This is done for all accidents that fall within the radius for each route. Clicking the spinner at the top right allows the user to see the safety rating for each route, as well as toggle between routes. Selecting a spinner item not only changes the displayed route, but also changes the directions displayed to the user. So here you can see we are displaying one route and its corresponding directions. And then if we change to a different route, you'll notice that the directions also change. Clicking on the list navbar icon displays a list of all stations. The user can select the search icon in the top right corner to filter for specific stations. Selecting a station returns the user to the map and displays an info window for the corresponding station. Lastly, clicking the profile navbar icon shows the user information about their profile, such as the total trips they have taken and the total distance traveled. This feature is still currently being developed, but we hope to be able to display neat statistics to the user in the future. Clicking the sign out button removes the user from the current session and returns them to the login screen. Next, I will briefly discuss the biggest challenges we face when developing our Safest Path app, which happen to be how to run calculations on a background thread. If you did not know, UI elements such as activities run on the main thread or the UI thread, and it is suggested that you run calculation-heavy tasks on a separate background thread to avoid freezing your application. After countless attempts, we still had trouble performing the calculations on a background thread, then updating the main thread once the calculation is finished. This has been the Android adaptation of our Safest Paths web app. Next, Haley will talk about our visualization and research app regarding bicycle accidents in the greater Los Angeles area.
Did you see these?
Another project we worked on is the bicycle collision visualization and research app. This was built with the ArcGIS, JavaScript mapping, and data visualization framework, along with Node Express JS and
Maybe you
Project
could just,
Engine.
oh, wear it backwards maybe.
Oh, yes, nice and plain on that side, huh? I like
Yeah.
it. No, no.
Hello, Julia. Would you mind silencing your microphone while the presentations are taking place?
I'm sorry, guys. Didn't know
No
I was.
problem. Thank you so much.
Okay, thank you. Continuing. The app visualizes bicycle collisions across Los Angeles. If you look at the map, the colored lines represent bicycle routes. There are 7 types of bicycle routes across Los Angeles, including lane, showered routes, paths, protected bike lanes, buffer bike lanes, and bicycle-friendly streets. The markers you see on the map represent clusters of collisions. There are about 10,000 accidents represented on the map. Without clustering, it becomes overwhelming very quickly. In the bottom right, you can see a legend using 2 different visualization techniques, including a gradient that represents collision time and markers that represent the collision severity. The least severe, collision severity 0 or property damage only, is the smallest marker. The most severe, collision severity 1, fatalities, are the largest markers. With these features, we hope to gain unique perspectives and identify patterns. Additional analysis is performed to understand collision rates along bikeways and off bikeways. Here we have 2 different filters that we implemented. One allows you to filter by the collision severity. On the left, we see only the large circles or the collision severity 1 fatalities. On the right, we filtered by the collision time. Only accidents that happen after 1700 or 5 p.m. are shown. In both of these examples, you can see how color represents time. The yellow on the left of the fatalities is early morning accidents, 12 a.m., 2 a.m., and so forth, while on the right, the after 5 p.m. accidents are all represented in blue. Furthermore, clicking on an individual accident will bring a pop-up that shows the accident statistics as gathered by Los Angeles GeoHub. Here we can see the accident happened in 2018, was a fatality, and happened at 2:10 in the morning. Additional features include being able to click along bikeway segments to understand how accidents intersect. Clicking on a bikeway segment brings a pop-up for the total number of accidents intersecting this segment, and importantly, shows if they happened before or after the bikeway segment was installed. Here we can see that there were several accidents that happened before installation. However, we only have 2 accidents that happened after installation. To better understand how these accidents happen and on a larger scale, a grid was implemented across Los Angeles. Clicking on each grid cell will bring up a pop-up with all the accident statistics for that cell. Here we see there are 450 accidents. These are broken down by collision severity and for accidents that are on a bikeway, whether it happened before or after installation. Additional information for each bikeway accident is provided as well. These results are all decomposed into about 110 features for each grid cell, which are then stored and then which are saved and then presented later in the app. Our summary and results. Collision severity rates per 100 accidents along bikeways compared to off bikeways. Collision severity 0, 2, 3, and 4 are all very similar. Collision severity 2, we do see a slight drop in collision severity 2 accidents along bikeways, meaning that there aren't as many collision severity 2 accidents along bikeways. Additionally, we were interested in the distribution of collisions across the different bikeways before and after installation. In Chicago, there was a study showing that the installation of shared routes resulted in an increase of accidents along those ways. Here, if we look at before the installation of shared routes, those segments only accounted for about 12% of those accidents. However, after the installation, we can see that it's almost 25% or a quarter of accidents. The accidents along bikeways are of shared routes. Another note of interest is protected bike lanes. Here, before the installation, these accidents along these routes were 33%. However, after a protected bike lane was installed, it accounted for only 2%, a drastic drop. Some of the challenges we faced in developing this app was the client-side calculations and performing geometrical analysis of the bikeways and the intersections. It is very intensive to perform client-side and takes time to produce results.
For this project, we were asked to implement the Metro Bike Share historical dataset found on the Metro website. As you can see here, this is a snippet of a dataset of quarterly transactions for all of July through September of 2019. There were about 90,000 records. We used Python to manipulate this data to create filters for our web map to show each station and categories of day of week and time ranges of transactions. With our map, we were able to visualize the most popular day for each station along with the peak hour for them. Each circle represents a bike station within the area of Los Angeles. The color of the circle indicates the most popular day. So the bigger the circle appears, the more bikes that tend to be used. The smaller the circle is, the least popular amount of bikes tend to be used. We were able to change the opacity of each circle to indicate the peak hours. The more solid each circle appears, the later in the nights bikes tend to be used, as well as the more visible circles tend to be the earlier in the morning the bikes are used. For more clarity, we created a legend to the right. On the map, you'll notice the positive or negative percentages near each station. This represents the usage increase or decrease of each station compared to other quarters. This will help us determine which stations are thriving better than others. Also, when you click or hover over a bike station, it will give you statistics for that specific station. We created bar graphs and charts that displayed the count of trips for each day of the week for that station. Also, small information regarding the total amount of trips originating, the peak day, and the peak hour. We also displayed counts of trips for each specified time ranges in that chart to determine popular times bikes are being used. We also narrowed our search so that we can filter through specific days of the week to give us data for just that day. Just like the last slide shown, the size of each circle determines the popularity of each station. Each color of the station represents a specified peak time for that day chosen. For example, if you were to choose a station with a dark blue color, that means the peak hour for that station is from 6 to 9 p.m. When you click or hover over a station, it gives us the number of trips for that day for the 3-month span displayed in a bar graph with a chart of average amount of trips for that day. It also gives you the percentage of trips for specified time ranges in a chart. With this data shown, we can determine which stations are going to be busy at specific times throughout the day. Some small features we implemented was a search bar for a faster search for stations using station numbers and station names. We also created a radio button so that you can switch back and forth for originating and ending trips. With this visualization, we hope to help Metro predict and officially put more bikes into stations that need them the most. Now Marcio will be discussing our mobile app development for Metro Bike Share historical data.
For our last project, we also started developing a mobile version for the Metro Bike Share data for Android. We implemented most of the main features and hope to be adding more in the near future. Just like in the previous project, the mobile version uses data gathered in the Metro Bike Share website, and then we visualize and analyze the data using the ArcGIS runtime SDK for Android. The layers you see there are categorized by color and size, just like in the web app. The color represents the peak day for the station, which is the day with the most trips, and the size represents the average amount of trip that each station has. A bigger circle means more trips have originated from certain stations. Pressing on the station displays information such as total trips, the station name, and its ID. You can also change the layers to be displayed by days of the week instead. This will change the color to represent the peak hours instead of the peak day, and size will mean the amount of trips that each station has for the day selected. We also added a query feature to our mobile app. With this feature, the user is able to search through our query and find a specific fields in our database. Some of the challenges that we faced when making the mobile version were that because none of us had an Android device, running the app through an emulator could take up to several minutes. Another challenge was because the API for the ArcGIS for the Android is not as developed as the API for the web application. We were only able to implement the basic features in the Android version. Now, going forward, these are the few features that we hope to implement in our apps. First is safety rating for the bicycle navigation, and then graphs for the Metro bike share Android app. Additional statistics for the accident visualization app, and we hope to make these apps public for people to use. Lastly, we would like to use more advanced AI and machine learning algorithms to predict patterns. Thank you, and that is the end of our presentation. We will now be taking questions.
Thank you very much. So any questions, any comments? Please feel free to unmute yourself and ask your questions. Or if you have any comments or suggestions for the future work. All right, thank you, everybody. Personally, I believe that the team has done a great job because if you noticed, well, in senior design project, usually 5 students are supposed to work on single project. In this senior design project, in fact, 5 students have been working on 5 different projects and developed some products that are like real life products and deliverables. And hopefully we will continue this project in future again next year. Thank you very much, everybody.
This is really impressive work. Thanks, everybody, and done under very challenging circumstances.
Thank you.
Thank you for that.
Thank you very much. Thank you so much, Ian, for your advice. Everybody in LADOT and LACT that helped us develop this project, and also for your support. And also Toyota Mobility Foundation, of course, for its support. All right, thank you, everyone. Please stay safe and have a good day.
Thank you.
Thank you,
Take care,
everyone.
everyone.